Hey everybody, BC Calc 8.1 on sequences. Our goals are to understand the meaning of a sequence, the convergence or divergence of a sequence, how to use the limit of a sequence and find it, as well as how to use L'Hopital's rule for finding a limit. So let's start with some basic definitions here. A sequence is a list of numbers written in a defined order. So example could be A1, A2, A3 up to AN. So this is like our first term, our second term, our third term, up to our nth term. Okay, and it's a function. It is, and its domain is the set of positive integers. So when we have a sequence a sub n, for example, 1 over n, a sub n comes out to be the set defined by 1 over 1, that's its first term, 1 over 2, that's its second term, 1 over 3, its third, all the way out to 1 over n, its nth term. Okay, so sequences are not continuous, however, they are functions. So sequences can be written as a sub n rather than f of n. So you could think of, like I have above, 1 over n as a non-continuous version of f of n equals 1 over n. So let's graph the two of those real quick and kind of look at the difference. Of course, n always starts at 1. So if I were to graph a sub n, here would be 1, here would be 1, not to scale clearly. Here would be 2, here would be a half. This is going to get kind of messy quick, so I'm not going to label the axes, but here would be the first 5 terms, right, of 1 over n. That sequence. Now, the function f of n equals 1 over n would look like the following. So you can see that the sequence is a portion of that function, and they're going to behave very similarly as n goes to infinity. Okay, so let's look at the definition of the limit of a sequence. A sequence has a limit L, means that the limit as n goes to infinity of a sub n equals L. Or we could say that as n goes to infinity, a sub n heads to L. So if I looked at the limit as n approaches infinity of 1 over n, in this case, that would approach 0. Therefore, as n approaches infinity, 1 over n approaches L, which in this case would be 0. Okay, so we're going to look at, and this might take you back to some year 1 AP Calc material where we were looking at limits specifically, and in this case at limits at infinity, which are like horizontal asymptotes. So you can see that the horizontal asymptote of the function 1 over n was y equals 0, and therefore you can see that the sequence is approaching the same. If a limit exists, then the sequence converges or is convergent. Otherwise, the sequence is divergent. So if there's a horizontal asymptote, what this is saying is if there's a horizontal asymptote for the function that matches the sequence, then the limit of the sequence exists, and therefore the sequence is convergent. So Theorem 2 says the following. If the limit as x approaches infinity of f of x equals L, this is our function f of x, not our sequence, and f of x is a continuous function, and f of n is equal to a sub n, when n is an integer, then the limit as n approaches infinity of a sub n equals L. Okay, so a cool example of this I actually like to think about, and I'll go over a couple convergent sequences and then a couple divergent sequences. So let's look at some convergent sequences first. So here are a couple of convergent sequences. A sub n is equal to 2n cubed plus 1 over 14 minus 5n cubed. So in this case, if I were to consider this to be a function that is continuous, okay, this would be continuous on the values from t greater than 0 up to infinity. Then what I could do is I could look at the limit as n approaches infinity of f of n. And clearly, based on some properties that we've looked at in past calculus classes, we could see that that would be negative 2/5. Negative 2/5. Therefore, by this theorem, theorem number 2, the limit as n approaches infinity of a sub n would also equal negative 2/5. Okay, let's look at a divergent sequence. And this one might be easier to visualize graphically, but let's call b sub n the natural log of n. Okay, so if you wanted to look at the sequence itself, b sub n would be the following. The natural log of 1, which is 0, the natural log of 2, which is a positive number, and the natural log of 3, etc. Now, the graph of natural log looks like this. Here, this is the point 1, 0, and there's a vertical asymptote here at x equals, I should say, n equals 0, but we'll go with x equals 0. All right, now, does the natural log have a horizontal asymptote? The answer to that is no. So if I called f of n natural log n, the limit as n approaches infinity of f of n actually doesn't exist, right? Therefore, the limit as n approaches infinity of b sub n also does not exist. Therefore, this sequence, b sub n, is divergent. There is no value that b sub n approaches. Likewise, over here, a sub n was thus convergent. All right, let's continue on to the next slide and look at a few more properties and laws for sequences. Okay, some limit laws for sequences, important to be aware of. And they're very similar to other laws that we've seen with derivatives, integrals, just, your properties of order of operations in general. So let's look at these rules. We've got the sum rule. The limit as n goes to infinity of the sum of two sequences is the limit as n goes to infinity of each of those sequences individually. Similarly with difference, as well as the product of a constant, right? So if I have a constant times a sequence, I can pull that constant out in front and just find the limit of the sequence itself. The limit as n approaches infinity of a constant is just that constant, right? As n gets really large, nothing's changing, right? The constant is the output. We got the product rule here. We got the quotient type rule here. Of course, that is if the limit as n approaches infinity of b sub n is not equal to 0. That would be a problem. And then a power rule here. This applies if p, that power, is greater than 0, and a sub n is also greater than 0. Okay, so back to some AP Calc stuff from last year. The squeeze theorem. The squeeze theorem for functions actually also works for sequences. Okay, we can use very similar properties to what we did with functions. So if a sub n is less than or equal to b sub n is less than or equal to c sub n for n greater than or equal to n sub 0, this just means that our first available value for n, then if the limit as n approaches infinity of a sub n is equal to that of c sub n, and they equal L, then that would force b sub n to also equal L as n approaches infinity. So a nice example we like to talk about at times is, let's say b sub n equals sine of n over n. So what would b sub n look like? Well, it'd be sine of 1. Okay, that would be our first term. Then it'd be sine of 2 over 2. Then it'd be sine of 3 over 3, which can be hard to visualize, right? And continuing on as n approaches infinity. Now, what we like to do with the squeeze theorem is we like to work with sine of n first. So we know that sine of n will always be less than or equal to 1 or greater than or equal to negative 1. Thus, sine of n over n will be less than or equal to 1 over n, which will be greater than or equal to negative 1 over n. Now, since the limit as n approaches infinity of negative 1 over n is equal to 0, and the limit as n approaches infinity of 1 over n is also equal to 0, then by the squeeze theorem, then the limit as n approaches infinity of sine of n over n will also equal 0. So that's the squeeze theorem. Theorem 4 that we have available to us here is that if the limit as n goes to infinity of an absolute value of a sequence equals 0, then so does the limit as n approaches infinity of the sequence. Okay, so for example, let's say a sub n equals cosine of pi n over n. Okay, so let's look at a few terms. Let's go first term, cosine of pi. Well, that'd be negative 1 over 1. Then it'd be cosine of 2 pi, which would be 1 over 2. Then it'd be cosine of 3 pi, which is negative 1 over 3, etc. Now, what you'll notice is that a sub n, if I take its absolute value, would actually be equivalent to 1 over n. And we know that the limit as n approaches infinity of 1 over n equals 0. Therefore, by theorem 4, since limit as n approaches infinity of the absolute value of a sub n is equal to 0, then the limit as n approaches infinity of a sub n should also equal 0. Okay, so you can kind of visualize this. Here's a sub n. First term is negative 1, then a positive half, then a negative third, then a positive 1/4, then a negative 1/5, a positive 1/6. You can kind of see how, this sequence itself may be oscillating in its sign, alternating in sign, but it is approaching 0. So the function, this is kind of interesting, but the function cosine of pi n over n, let's look what that would look like. Cosine of pi n over n. Let's just start at 1 to keep it simple. It would kind of look like this. Oop, I bumped it there at the end, but what you can see is that it's eventually approaching a horizontal asymptote of 0. Okay, let's look at examples 1 and 2 now, and then we'll continue. So the limit as n approaches infinity of n over n plus 1. Now, if you were to just do a direct substitution, you would see an indeterminate form. And when working with limits, if you get this indeterminate form, infinity over infinity, what we can do, as long as the sequence is in function notation, is that we can evaluate this by using L'Hopital's rule. Now, there's a couple other ways to do this. What we could do is we could take the limit as n approaches infinity and divide everything by the highest powered term in the denominator, which in this case would be this n. So I divide by everything by n. Okay, which would allow me then to do a direct substitution after I simplify. This would be 1 over 1 plus 1 over n. If I then did a direct substitution, I'd get 1 over 1 plus 0, right? Because this 1 over n limit as n approaches infinity of 1 over n equals 0. So it looks like my limit, my sequence limit would go to 1, okay? But how about an example here where that wouldn't necessarily work out so well? Example 2. So what I would do is I would redefine f of x, or f of n, as ln of x over x. And then you can use L'Hopital's rule in a moment here. Limit as x approaches infinity of ln of x over x. Well, what I get is that the limit as x approaches infinity of ln of x approaches infinity, and the limit as x approaches infinity of x approaches infinity. Therefore, by L'Hopital's rule, then the limit as x approaches infinity of ln of x over x should be equal to the limit as x approaches infinity of the ratio of their derivatives. Okay, so the limit as x approaches infinity of 1 over x over 1. Well, the limit of the numerator will be 0, the limit of the denominator will be 1. Therefore, our original limit will equal 0. That tells me that as n grows toward infinity, the rate of change of natural log of n is overpowered by the rate of change of the sequence n. Okay, so we can use L'Hopital's rule using Theorem 2 and turning it into a function in order to evaluate the limit. Seeing that now the function would be continuous everywhere at x equals 0. So f of x is continuous when x is greater than 0, which is great because when we work with a sequence, our sequence starts with n equals 1 and so on. Okay, let's continue with some more sequence work. Okay, let's look at example 3. Example 3 says, is a sub n equals negative 1 to the nth convergent or divergent? Okay, so let's look at a sub n expanded. Well, that'd be negative 1 to the first, which is negative 1. Negative 1 to the second, which is 1. Negative 1 to the third, which is negative 1. Negative 1 to the fourth, which is 1. That pattern will not change. It'll continue in that way forever. Therefore, this would be divergent. Okay, you can see it graphically as well. Okay, let's look at it. So here is 1, here is negative 1. Here's our first, second, third, fourth, fifth, sixth, all the way out. Our first term is negative 1, then positive 1, then negative 1, then positive 1, then negative 1, then positive 1. That'll continue. Okay, that will not converge to anything because as it approaches infinity, there is no convergent value, no horizontal asymptote, so to speak, on the function. Okay, let's look at example 4. In example 4, I would consult Theorem 4. And Theorem 4 says that if the limit as n approaches infinity of the absolute value of a function or a sequence equals 0, then the limit of that sequence would also equal 0. So I'm going to take the absolute value. First, I'm going to call a sub n this alternating sequence. So the absolute value of that would actually be 1 over n. So I'm going to take the limit as n approaches infinity of the absolute value of a sub n, which of course we've looked at already, will equal 0. Therefore, by Theorem 4, and you don't have to state Theorem 4 when you're writing this out later on, it's just I'm referencing it now, so you go back and check it out. Therefore, by Theorem 4, the limit as n approaches infinity of a sub n would also equal 0. So this sequence a sub n is convergent, okay, or converges to 0. Above in example 3, I should have said a sub n is divergent, excuse me. Let's look at proving that a sub n, which equals n factorial over n to the nth, converges to 0. We're given a little bit of a guide here, seeing that we know where this is headed. Let's write out a few terms. a sub n would equal n times n minus 1 times n minus 2 times n minus 3. Now this is all part of one term. Okay, that's the definition of n factorial. Okay, n to the nth would be n times n times n times n, all the way down to n times n times n. So there are n terms in the numerator. There are also n terms in the denominator. Okay, so if I took the limit as n approached infinity of this ratio, right, of a sub n, what would that equal? Well, I'm saying it converges to 0. Let's prove why. Okay, so it doesn't matter really how many terms there are. Okay, let's look specifically at how the numerator compares to the denominator. Okay, so what I'm going to do is I'm going to take this sequence and I'm going to show it's less than something that converges, and I'm going to show it's greater than 0. Okay, now I'm going to show you what this thing is that's greater than this sequence for all terms and also converges. This is kind of a squeeze theorem type work, right? So if I can show that the limit as n approaches infinity of 0 is equal to 0 and is equal to the limit as n approaches infinity of this thing is equal to 0, then what I know is that the limit as n approaches infinity of n factorial over n to the nth will also equal 0. So that's where I want to get at the very end. So let's do a little work on this. Okay, so check this out here. I've got 1 over n. There's 1 over n. Okay, so let's put that right here. Okay, and then I've got 2 over n. Okay, 2 over n. And I've got 3 over n. 3 over n. And I've got, oh, I'm running out of colors, n minus 3 over n. So let's do a little ellipsis here. N minus 3 over n. See if I got any more colors. There we go. I got one more. I got n minus 2 over n. And I've got n minus 1 over n. And then I've got n over n. Okay, I know that this is going to be greater than 0 because n is always positive, right? So that'll be greater than 0. Okay, greater than 0 since n is greater than 0 and n is in the positive integers. Okay, so this thing constructed right here will be greater than 0 since n is in z plus. Okay, now I want to show that it's less than, and I'm going to show it's less than 1 over n. That's the thing I'm going to compare it to. Let's show that it's less than 1 over n. Well, n over n is going to be equal to 1. N minus 1 over n will be something less than 1. So will n minus 2 over n. That'll be less than 1. This will be less than 1. This will be less than 1 and less than 1. So if I multiply 1 over n by a bunch of stuff that's less than or equal to 1, then it'll be less than 1 over n. Okay, for example, let's say n equals 6. So this would be 6 over 6 times 5 over 6, right? So 6 over 6, 5 over 6, 4 over 6, 3 over 6, 2 over 6, 1 over 6. Okay, that's going to be less than 1 over 6, right? You can see that as I multiply 1 over 6 by all of those, it's going to be greater than 0, and it's going to be less than 1 over 6. So this 1 over 6 right here, right there. Okay, thus, I know that the limit as n approaches infinity of 1 over n is equal to 0. Therefore, this is not a formal proof, it's just kind of an informal proof, if you will. I've now shown that the limit as n approaches infinity of n factorial over n to the nth is equal to 0. That tells me that n to the nth will overwhelms n factorial as n approaches infinity. Okay, that's good for part 1. We'll see you in the next video.